For this lesson, we're going to be looking at how to calculate different probabilities using counting techniques. So when we're determining probabilities, we need to consider how to calculate the total number of possible outcomes, as well as the number of outcomes for a particular event. To do this, we often need to use our counting techniques that we learned in Unit 1. So this gives you an opportunity to see why we did everything in Unit 1 and what the point of all of those lessons really was. So we'll do a couple of examples. This first one here says determine the probability that Logan will win a race and Brian will finish second if there are 7 runners in the race. The first thing that we want to consider when approaching any question is, does order matter? Now, because Logan is first, Brian is second, that is an indication that order does matter here. If Brian was first and Logan was second, that would be a totally different outcome in this situation. Therefore, order matters, and this is a permutations question. So as we go through, we're going to do 2 methods to solve this. I think the first one is the one that most people would use. However, the second one is just a bit of a different approach, and some people might really find it a little bit simpler. So with our first one, we need to determine the probability that Logan will win and Brian is second. So let's start by identifying our event. So we're going to let event A be Logan getting first and Brian getting second. Now we need to determine the number of elements in our sample space or the total number of outcomes for this situation. Now there are 7 runners, so someone coming first, second, third, fourth, fifth, sixth, or 7th. Because order matters here, we have 7 choices for first, 6 choices for second, 5 choices for third, and so on and so forth. Now, because we require a first place, a second place, and a third place, and a fourth place, we multiply, and that will give us 7 factorial. Now, in order to calculate probability, we also need the number of elements in our event space, or in other words, the number of ways event A can happen. So again, I'm going to write out my 7 spaces. 1, 2, 3, 4, 5, 6, 7. Now we have a few restrictions this time around. We must have Logan in first here, so there's only one way to do that. Then we must have Brian in second here. Only one way to do that. Now, for the third place spot, we have 5 different people who could get third, then 4 different people who could get fourth, and so on and so forth. Now, just like before, we need a first place winner and a second place and a third, so we multiply, and that will give us 5 factorial. So now that we've determined those 2 values, we can find our probability of event A, which is the number of elements in A, divided by our number of elements in the sample space, or the number of ways A could happen, divided by the number of total outcomes, which is 5 factorial, all over 7 factorial, which gives us a total of 1 over 42. Now, as always, you can write this as a fraction, as a percent, or as a decimal, whatever works best for you, unless it specifies somewhere in the question. Okay, so that's our first method. Now let's try another method. For our first method, we considered all of the different spots. We considered all 7 places of this race. But we only really care about first and second, because those are really the only ones where we're adding restrictions in. It doesn't really matter who gets 5th, 3rd, 4th, any of those. So for method 2, let's just look at first and second. So again, we'll define our event. So we'll let event A B, Logan in first, and Brian in second. There we go. Now let's determine our number of events in our sample space. Now, there's two ways we can do this. We're only looking at first and second here. Because we're only looking at first and second, there are 7 people who could get first, 6 people who could get 6 people who could get second. So that is the same as 7 permute 2, which will give us 42. Now again, we need to find the number of elements in our event space, or the number of ways that event A can happen. So again, we're only looking at first and second place. Now there's only one way to pick first, because that must be Logan, just like before. And only one way to pick second, because it must be Brian. So that gives us 1. So the probability of event A, number of elements in our event space, or the number of ways A can happen, divided by the number of elements in our sample space, or the number of ways all of the outcomes can happen. So that gives us 1/42. So it doesn't matter how you approach this, and it's completely up to you, but it is beneficial to see some different options and some different ways to approach things. Now there's a little note at the bottom here. Really important, you highlight, circle, underline it. If order matters, permutations, just like this question. And if order does not matter, we use combinations. And that nicely brings us to our next example here with some combinations. So here's our situation. A drawer contains 4 blue socks, 7 white socks, and 6 black socks. We're going to draw 3 socks at random from the drawer. So to start, you think to yourself, does order matter here? Because I'm reaching my hand in and just grabbing 3, the order in which the socks are in my hand doesn't matter, because I'm just looking at a group of socks. So that means we can use combinations here. So let's start with this first one. What is the probability that all of the socks are black? Let's start by identifying our event. So we'll let A be all black socks. Okay, so let's start by finding the number of total outcomes, or the number of total elements in our sample space. So in total, we have 4 plus 7 plus 6, which is 17 socks. And we're going to be choosing 3 of them. Now for the number of ways our event can happen, we want 3 black socks. So if I look, there are 6 black socks, and I want to choose 3 of them. So now that I have those 2 values, I can find my probability of event A, which is the number of ways A can happen, divided by my total outcomes. So we have 6 choose 3, divided by 17 choose 3. That will give us 20 over 680, which reduces to 1/34. Now again, you could absolutely put this in a decimal, a percent, because it doesn't specify in the question. Really up to you, however you want to write your answer. Okay, let's try another one. So for this example B, we want to determine the probability that 2 socks are blue and 1 is white. So let's start by identifying our event. We'll let event A be 2 blue and 1 white. Again, let's determine our total number of outcomes, or the number of elements in our sample space. Just like before, we have 17 socks total, and we're choosing 3 of them. Now for the number of elements in our event space, or the number of ways A can happen. We want 2 blue and 1 white. So out of our 4 blue socks, we're going to choose 2. And so we multiply. Out of our 7 white socks, we're going to choose 1. So now that I have that, I can find my probability of event A, which is the number of ways A can happen, divided by my total number of outcomes. So we have 4 choose 2, multiplied by 7 choose 1, all over 17 choose 3. This will give us 42 over 680, and that will reduce to 21 over 340. Again, you can leave it as a fraction, you could make it a decimal, you can make it a percent, doesn't matter. Okay, so there's 2. So now I want you to take a moment, pause the video, give the other 2 a try on your own, and then we will take it up. Once you're done, just press play again, and then see the solution. So for number C, first define your event. Our sample space is going to be the same. Now for our event space, or the number of ways we can pick no white socks, if I count above, we have 4 plus 6 socks that are not white. So out of the 10 not white socks, we're going to choose 3. So probability of event A will be number of elements in A divided by our number of elements in our sample space, which is 10 choose 3, all over 17 choose 3. And that will give us 120 all over 680, which is 3 over 17. Again, you can write that as a fraction, decimal, percent, whatever works. Now for example D, what is the probability that we have at least one blue sock? So we'll start by defining our event. Now be mindful of the wording here. It says at least one blue. Now this means I could have 1 blue, I could have 2 blue, or I could have all 3 being blue. So we have a few different cases that we need to consider here. So to start, our sample space is still 17 choose 3. That hasn't changed. Now for the number of ways we can have A, we could have where we choose 1 blue sock. So out of the 4 blue socks, we're going to choose 1. And then out of the remaining 13 socks, we're going to choose 2. Because we still have to pick 3 socks total. So we could have that case where we get 1, or we could have this case where we pick 2 blue socks. So out of the 4 blue socks, we choose 2. Out of the 13 other socks, we choose 1. We could have that case, or we could take the 4 blue socks, choose 3, then out of the 13 others, choose 0. So now to find our probability, we take this long thing, 4 choose 2, 13 choose 1, 4 choose 3, 13 choose 0, and divide that by our sample space. And when you put all of that into your calculator, you will get 394 divided by 680, which reduces to 197 all over 340. There we go. So now that we've done those 2 examples, let's try a bit of an interesting one. So this next example is just for fun. It's called the birthday paradox, and it's a bit of a surprising outcome. It's something that you won't think is going to happen, but the probability can be a little bit surprising. So what we're going to do is we're going to determine the probability that 2 or more people in our class have the same birthday. So what's the probability that if we asked the whole class what their birthdays were, that at least 2 people would say the same day? Now, while we approach this, we are going to just disregard leap years, disregard possibilities of twins, anything like that. And we're just going to think about the number of people and the possible days in a year. So let's start by defining our event. So we're going to let event A. Now, we have a few options here. It is easier to find how many people have totally different birthdays. So once we define our event A, then we can start looking at our complement. So we'll let event A be at least 2 people have the same birthday. Again, that can be kind of hard. There's a lot of combinations there. So it would be easier if we found the probability of a complement or the probability of everybody having identical birthdays. So let's start by finding the number of ways a complement can happen. Now for our purposes here, we're going to say we have a full class. We're going to say that we have 30 people. So we're going to look at all 30 people, 1, 2, 3, and then we would draw 30 lines. Now we want to determine the probability that everybody has a different birthday. So for the first person, there would be 365 options for them. Then for the second person, they can't have the same birthday. So there would only be 364 options. Then for the same reason, 363, 362. Then we would have 30 lines and you draw them all the way down and we would get 336. Now because we need a birthday for the first student and the second and the third and the fourth all the way to the 30th, we multiply. Now you can write it out like this, but this is also just a permutation, so we could do 365 permute 30. And either way, you will get 2.17 times 10 to the 76. So it's a giant number, which makes sense. There's lots of ways to assign birthdays to 30 people. But that is the number of ways where everybody has totally different birthdays, no overlap. Now for our total outcomes, or the number of elements in our sample space. For our total outcomes, everybody could have the same birthday, whatever birthday they want, no restrictions. So our first person would have 365 options, so would the second, so would the third, so would the fourth, all the way to the 30th. Because it doesn't matter what day they pick, it can be whichever day they want. Now because we need the first student and the second and the third all the way to the 30th, we multiply those, so that will give us 365 to the power of 30, which is 7.39 times 10 to the 76. Now we can find the probability of a complement. That is the number of elements in a complement, which is 2.17 times 10 to the 76, divided by the number of elements in our sample space, which is 7.39 times 10 to the 76. And that will give us 0.29. Now that's for a complement, the probability of everybody having different birthdays, but we want to see the probability of at least 2 people sharing the same birthday. So to find the probability of A, we do 1 minus the probability of a complement, 1 minus 0.29, which is 0.71, or 71%. So in a group of 30 people, there is a 71% chance that at least 2 of them have the same birthday, which is a bit surprising, I think. Okay, so for homework here, there is some textbook work. That's just this stuff here. And then there is this worksheet here. Now I know that this is a lot, but try your best and we can take up a bunch tomorrow. These ones here on the worksheet do get a little tricky, so do your best, take it nice and slow, but definitely let me know if you have any questions.